Okay, this is going to be the fourth and last video for the foundation rules for probability in chapters 14 and 15 for AP statistics. There's a couple of odds and ends and things to just tie everything up that we need to talk about that will help make it possible for us to do problems. One thing about probability is, unlike the big word problems that we've dealt with up till now in AP stats, usually the way to compute the answers here is real quick and simple to do once we identify the strategy. But what makes this hard is that there's a lot of different rules and a lot of different strategies. So we have to learn to see patterns in what things are the best method to apply to solve a problem. And sometimes there's more than one way. So by kind of tying it up, it helps us to see that. But we're just going to have to get a lot of practice in order to become good at it ourselves. Okay, a little bit first more about conditional probability. Now that we've defined and, we can say more about conditional probability. Right, we know that conditional probability is the probability that's computed within only a part of the sample space that meets the condition. So if I want to find the probability of some event B happening given that A happens, the bottom of the fraction is going to be A, right? So if I had a Venn diagram representation, it would be this part of the sample space that I've got shaded in blue. And then the part that would be the numerator, all of A, right? And then the denominator. The numerator would be the part within that circle that is the event B, right? So if this is B, it wouldn't be all of B, it would be the part of B that's inside the conditional sample space. So it represents that. But if I draw it like this, we can see that that numerator is really an overlap. So it is really the probability of A and B both happening, right? So if I wanted to kind of replace these with notations, right, the probability of B given A is the numerator is the probability of A and B, and the denominator is just the probability of A itself out of the entire amount. So this right here is called the conditional probability formula. Now, a lot of times in earlier math classes, especially in the algebra classes, when conditional probability is taught, it's taught with the formula, right? So, but I've taught it here a different way, which is draw out the sample space, circle the area in the sample space that's the denominator, and then staying within that, just pick out the part on the top. I have found it's much, much less error prone to do it that way, to calculate conditional probabilities, to think of it as a subset of the subset, which is a part of the sample space. So you've got the sample space here, you've got the conditional sample space, which is a subset of that, conditional sample space. That's the bottom of this fraction. And then within that, the subset within the subset is the numerator. That's the event, okay? But you can use this formula, and if you feel comfortable using it from the past, you're welcome to do that, okay? I just want to show how that formula connects to the way we've been doing it. Okay, but what I'd like us to do in the class really is to just think of it as, regardless of how you've listed this out, you can calculate any simple or compound probability or conditional probability. So I'm going to make a table here where we're just going to calculate these probabilities for 3 different sample space listings. And what I have is the exact same data here, but listed with different ways to list the sample space. So this is about gender separated data on whether people prefer regular or diet soda, okay? 100 people polled, and this is a table listing. This is a Venn diagram listing, and this is a tree diagram listing, and this is a Venn diagram listing. If you look at this, they're actually all the same. For example, let's just take this one branch right here, okay? So this is, given that we're talking about males, what's the probability that they like regular, right? So within the 40 males, 16 out of 40. That's why this branch probability is labeled that way. So we've got counts here, we've got counts here, we've got branches labeled with probability here, but they're all the same data, just listed differently. What we're going to find when we work a lot of examples is we're going to talk about how do you pick the best way to list the data. Once you've got the data listed, then you can compute things, okay? So let's just practice computing things in different ways. And you can pause the video and try these things. I'm just going to work through carefully how to calculate with each of these with the different methods, okay? And I'll try to show on the diagrams over here what I'm doing. Okay. So if I want the probability of male and I've got the table, then that means I'm taking all the males out of the entire. So I've got the entire table and I've got the males within that. So it's going to end up being, out of the entire table, which is 100, I've got 40 in that one row. So it's this row divided by the total, and I've got some numbers on the side that help me quickly compute that, okay? If I had a tree diagram, how would I find the probability of male? Well, the probability of male is just that they take this first branch. Everything after this point is this out of this whole thing, right? So the probability of getting to here out of the whole tree is just the probability that we take that first branch. So right on the tree, it's got the answer. It's 40%. And for the Venn diagram, it would mean out of the entire Venn diagram, where I would have to add up these numbers, 26 plus 16 plus 18 plus 42, how many of those meet male? Well, male is everything outside of the female circle, so that would be these numbers. So 24 plus 16 out of that total. And if you add that up, that's 40 out of 100. So you can compute that regardless of how you have this set up. You can compute that probability. All right, let's do that for these other probabilities as well. Okay, so for the second one, we're going to look at a conditional probability. What's the probability that somebody prefers diet soda given that they're a female? So if you're in a table, you're restricting yourself to just the females, and then you're saying how many of those people are diet, the subset within the subset, 42 out of the total 18 plus 42, which is 60 we have out there. So it'd be 42 out of 60. Okay, on the tree, it would be, okay, given that female has happened, that means you have taken this branch, and that means you're here. So this is the conditional sample space. Now, what's the probability that they pick diet? That's just the probability that they took this branch, and that's already labeled. It's 42 out of 60. Okay. And then down here, it would be, what's the way to represent the conditional sample space? That would be the female bubble, which is 18 plus 42. And then out of that, how much of those people like the diet drink? Well, it's 18 or 42, but the 18 people prefer regular. So these people over here must be the diet people. So you get the same 42 out of 60. So what I want you to see here is that no matter how you list it out, if you just think of it as identify the denominator as a conditional sample space, and then take the part inside that means the event, you can always come up with the answer. Okay. Let's do a few more. Let's do this one. So what if I wanted to find probability of diet given male? Well, same calculation, except we would just stick with the male part. So out of the total of 40 in the male for the tree, right, diet is 24. So it'd be 24 out of 40, right? And for the tree diagram, we would say, okay, we've taken the male branch. So now that I'm here, I'm in this part of the conditional sample space. What's the probability that I take the diet path? It's labeled directly 24 out of 40. And then for this, it would be the probability of males, or diet given males. So we have to identify the conditional sample space. Male is everything outside of female. So this is the conditional sample space, 24 plus 16. And then the diet people are the ones not inside the regular. So 24 out of that, also 24 out of 40. Okay, so you can see how this works. Okay, we're going to do a few more here. Let me switch to red because it's harder to see black. What's the probability of diet and male? Now, there's no line here, so this is a simple probability, and that means we're talking the entire table, but we have to include people that are diet and male. So the only ones that are diet and male are these 24. They're in the diet intersection of the diet and the male column. So 24 out of the 100, right? Okay, and then what about the tree? Well, the tree would be out of the entire tree, right? So the entire tree, that's the first thing. It's a simple probability, but they have to have diet happen and male, which means, well, we had male first. They have to take the male path, and then they have to take the diet path and get to this point on the tree. So we're at this point. But to calculate this, we know that we have to multiply as we go across the tree. So it's going to be 40 out of 100 times 24 out of 40, and those will cancel and give me the same 24 out of 100. Okay. For the Venn diagram, it's going to be out of the entire group. So the denominator is the entire 100 here. It's going to be how many are both diet and male. And we know that this symbol means intersection. So it's the intersection of diet and male. Well, diet is this part, right? And male is everything outside of here. So that would be this. And so it's the intersection of those two things. It would be this 24. So it's going to be 24 out of 100. And in all cases, we get 24 out of 100. Okay. All right, we're going to do a few more here. 2 more to be specific. All right. So let's say we wanted to find the probability that somebody likes diet, right? That's a simple probability. No condition is specified, so it's the entire table, 100. And then diet would be all the diet people, which is 66 out of 100, right? Okay, for the tree, that would be the entire table, right? But we have to get to diet somehow. And if you look at diet, that occurs here and here. Okay, so how will we get to that? Well, that means we first have to find these probabilities. So let's find those probabilities. Let me erase this. To get to here on the tree, we have to go this path and this path. So that's going to be 60 over 100 times 42 out of 60, right? Which is going to end up being, well, I'm going to write it that way. And then to get to this place, which is also diet, I have 40 out of 100 times 24 out of 40. And then because it's this or this, so this is and, remember we multiply to do and, but then we have this or this, so we will add. So to do the tree, we would have to take 60 out of 100 times 42 out of 60, and then add 40 out of 100 times 24 out of 40, which is going to end up being 42 out of 100 plus 24 out of 100, which turns out to be 66 out of 100. So you would need this to calculate that with the tree. So the tree is the hardest method here. And then for the Venn diagram, the diet is just out of the entire group, which adds up to 100 out of the entire group. How many of those are diet? Well, diet is everything that's not in the regular circle. So it's these things here, these two things added together, 24 plus 42, right? So depending on how you've listed it out, in some cases it's very easy to find, sometimes it's harder. Okay, we're going to do another conditional probability, but this time it's going to be the reverse of one we've already found. We found on this one, we're trying to find the probability of being a female given diet, and we already found probability of diet giving female, but we know that this matters, right? So for example, on the tree, right, to find the probability of diet given female, if you know you're already here on the tree, then the probability is just 42 out of 60 of taking that branch. What if I reverse this going this way? So it's easy to do with the table. I just specify the diet as the conditional sample space. So out of the 66, the probability that are females is 42, okay? And it's easy to do with the Venn diagram, right? Because I would just say out of the diet people, which is these people that are not regular, so that would be 24 plus 42. What's the probability then that that we get that they're females? That would be this 42, right? So you'd get the same thing. This computation is much more involved because what we'd have to do is find a way to list out the conditional sample space, and the conditional sample space is diet, which is strung out here and here. So it's kind of like the conditional sample space is this plus this, and then within that we're going to choose the female one, which is the path that went through F. So it's going to be this over these together. Okay, in fact, let's compute that real quick. Well, you know what? I think I have this on actually on the next screen. So since this particular situation occurs frequently, let's analyze that in more detail. Okay, if we're finding diet, right, to get to diet, it's actually, let me use blue for kind of consistency. That's here and here. So the probability of getting here is 60 out of 100 times 42 out of 60. And the probability of getting here is 40 out of 100 times 24 out of 40, right? So I've got these two things. And that means that the bottom of this is going to be the total number of paths to get through the tree to get to diet, to meet the condition. That's going to be 60 out of 100 times 42 out of 60 plus 40 out of 100 times 24 out of 40. Okay, but then in the top, we want to find just the ones that meet the event criteria of female, right? So female would be this particular path, so this one. So it's going to be the 60 out of 100 times 42 out of 60 over this. And if you carefully do all this out, right, let me actually show the math being done here. So the 60s cancel and you're left with 42 out of 100. And over here, the 60s cancel and you're left with 42 out of 100 plus these 40s cancel 24 out of 100, which turns out to be 42 out of 100 over 66 out of 100. And then if you divide or multiply top and bottom by 100, you get that same 42 out of 66 that we got before. Okay? So this is called a Bayes formula problem because the person who originally realized this, that if you set things up in a tree like this, it's very easy to find the probability of diet given female. Because if diet is the condition, if female is the condition, then you're here on the tree, and then the probability is just right there on the branch. It's 42 out of 60. But if you want to go backwards through the tree, if you want to go backwards and say, what's the probability of being a female, given that you have multiple n things here for diet, then you have to have this structure. So I think of it as take all the n probabilities and sum up the ones that are in the conditional sample space, and then pick the ones on the ends that meet the criteria for the event. So this particular structure is called a Bayes formula problem because of the first person who discovered that. So some conditional probabilities are right on the tree if they happen to be the second branch, but if you have to go backwards, you have this much more complicated structure. All right. All right, let's take another example of this and show how powerful this can be. Let's say that we have this situation here. So I'm going to make this much smaller. So let's say a test exists to detect cancer. And in people who have this test, the test correctly detects cancer 95% of the time, but it fails to detect the cancer 5% of the time. In people who don't have the cancer, the test correctly reports the cancer in 90% of the cases as not having it, but there's a false positive 10% of the time. And then long-term data shows that this particular cancer occurs in 10% of the population. So if a person takes this test once and cancer is detected, what's the probability that they actually have cancer? So we're trying to find this probability. What's the probability that somebody actually has cancer if we have a positive test? Okay. All right, so we're going to have to somehow come up with a way to list this out, and but we have to use the numbers in the problem. So one thing that we're going to study more as we just work problems is when you have probabilities or percentages given, usually the tree diagram is the best way to enter it, because if you consider this back over here, right? Tables, sometimes probabilities, but more frequently counts. Venn diagrams most frequently counts, but probabilities are always on the branches of a tree. So if we're given probabilities, a lot of time the tree is the best way to list things out. So let's actually do that. The first thing that would happen is someone actually would maybe have cancer, right, or not have cancer. So either we have somebody who has cancer or somebody does not have cancer. I'll use the symbol for not cancer. And then they take a test, right? And the test could be positive or the test could be negative, okay? All right, so let's fill in the probabilities that we have in the problem. It says if a person has cancer, then the probability that they test as positive happens 95% of the time. So that's the branch probability here, the conditional probability. Given that they have cancer, there's a 95% chance of a positive test and a 5% chance that the test misses it. But if they don't have cancer, 90% of the time it correctly reports that, but there's a 10% false positive rate. So you see how a tree allows us to directly enter these numbers right on the structure. So this is a great way to list the sample space. All right, so now what we're trying to do is to figure out what's the probability that given someone's positive that they have cancer. So the conditional sample space is all the positive results. That's these two. So I'm going to have to figure out these branches. Now, before I can do that, I have to multiply across here. So we're missing something. It does say that 10% of the people overall have cancer. So this is 10%, and therefore this would be the other 90% of people. All right. So if I calculate all these probabilities, in fact, let me just find them for all, right? To go across these and probabilities. This is 0.1 times 0.95. This one's 0.1 times 0.05. This one's 0.9 times 0.1. And this one's 0.9 times 0.9, right? I just multiplied across each of the branch paths to get here. And if you were to add all these up, they will add up to 100% because this is the complete sample space. All right, so we're going to say staying within the conditional sample space of people who are positive, that's just this and this. So this right here is the conditional sample space, and that means we're going to have 0.1 times 0.95. Since it's this or this, we'll add these two, plus 0.9 times 0.1. And then out of that, we want the ones that meet the event criteria that they have cancer. This path went through cancer, so this one is the cancer path. So this is the structure that would allow us to use conditional probability to calculate this, and it's a Bayes formula because it's actually reverse conditional. So if you compute that out, that turns out to be, shockingly, 5135. So given this test, which 95% of the time tests right for detects the cancer and only has a 10% false positive rate. If you test positive, there's actually only a 51% chance that you have this cancer. It's crazy, right? Usually people are shocked by this result, that this is so low. So what would we do if you were a doctor? Would you then, based on this one test, start aggressive chemotherapy or surgical intervention? Probably not, right? So there's a really quick fix to that. What would happen if I just had the person get a second test? Now, if I had them get a second test, then we're going to add more detail to our tree here. So let me add on more things here. Okay, so we have a positive test or a negative test the first time, right? All right, but then if they have a positive test, we're going to give them another test just to be sure. Okay, but we'll only do that in the case where they have a positive test. If they're negative, then we won't. Okay, so that means that now I'd like to say if a person who tests positive undergoes a second test, which is also positive, now what's the probability that they actually have cancer? So what's the probability that they have cancer given that they had two positive tests? Okay, so let's find all the probabilities here on the ends here for all the paths that get to the ends. This one here would be, well, we'd have the same chances, 0.95 and 0.05 here. If somebody did not have cancer, there's a 10% chance they test positive and a 90% chance that they correctly test negative. So this probability here is 0.1 times 0.95 times 0.95. And this one is 0.1 times 0.95 times 0.05. And we could have this cancer and negative. This is 0.1 times 0.05. And this branch here is 0.9 times 0.1 times 0.1. And this branch here is 0.9 times 0.1 times 0.9. And this branch is 0.9 times 0.9. And if you were to add all 6 of those outcomes up, those add up to 100% because that's all the things that can happen in the scenario. So which of these qualify as conditional sample space? They have to have both positive tests, right? Okay, well, out of all 6 of these outcomes, the ones that are both positive is this one and this one. So we'll add those up. We would have 0.1 times 0.95 times 0.95 plus 0.9 times 0.1 times 0.1. And then which ones meet the criteria for having cancer? Only this branch here that went through cancer. So it's the 0.1 times 0.95, 0.95. And if you compute that out carefully, that turns out to be 0.9093. So giving a second test, if they're both positive, now there's about a 91% chance that the person actually has cancer. And if you add it on a third test, it would go even higher, close to 99%. Okay, so no test is perfect, as we're seeing now, because this is being recorded during a pandemic, that, you know, tests have false positives and false negatives. It's the way it happens. But doctors get around this by requiring a second test, because even in fairly good tests, right, your confidence level that somebody actually has the disease can go from 51% all the way up to 91% just with a second identical test. All right, so that's let's just summarize what we know about probability here then. We know that there are, I wanted to mention one more thing before we summarize. What's the difference between independent events and disjoint events? Because people get confused, right? So disjoint events, or also known as mutually exclusive, that has to do with the or case. Independent events have to do with and case. Okay, so this is whether or not the probability of one is depending on the other, and disjoint has to do whether or not the two things can occur at the same time, right? It turns out, interestingly, that if you have two events that are disjoint, it turns out they can't be independent, right? Because here's an example with events that are independent or that are disjoint. So if I have a 30% chance of A happening and a 60% chance of B happening, and that's 90%, therefore there's 10% chance of neither happening, right? But there's no interaction here. There's no joint probability. Then how would we test for independence? Well, if you made a tree diagram of that same thing, right? If A happens, then there's a 0 chance that B happens because there's no part of A that contains B, right? But if A doesn't happen, in other words, if B happens, right, then what's the probability? Or sorry, if A doesn't happen, what's the probability that B happens? Well, A not happening would be this, right? And B, sorry, I get that wrong here. Let me back up. If A not happening is this, and B is only some part of that, so it would be 60 out of 70%, which actually I think this is incorrect. So let's figure out what that is. 60 out of 70% would actually be 0.85, 0.15. Okay, so the point is these are changing, because if these are disjoint, the probability of, if one event happens, the other one's probability is forced to 0, and yet the probability of B happening is not 0. That means that there's no way that mutually exclusive or disjoint events can be independent, right? So if there's separation, they have to also be independent. Likewise, if two events are independent, there's actually no way they can be disjoint, because the only way two events can be independent is if the probability on the second part of the tree is staying the same. And if that's true, then that means there is a branch probability at the top, right? So there is a and B happening. This is not 0 out here, so there's got to be a probability in the middle. So this is not a super important point, but just an interesting observation that although independence and disjoint events are two completely separate things, one's related to and one's related to or, if events are independent, they can't be disjoint, and if they're disjoint, they can't be independent. All right. Let's talk summary of probability here. So first, we know there's different ways to list a sample space, and sample spaces is some way to list all the outcomes. Sets, where we list everything out, or like a picture of a card deck. Tables, Venn diagrams, trees. In general, when you have probabilities, if probabilities are given in the problem, often we use Venn diagrams, because, not Venn diagrams, tree diagrams, because the tree diagram has the branch probabilities are always, the branches are labeled with probabilities. So a lot of times you can put that right on the tree. Okay, you can use the middle school formula that the probability of something is the number of desired outcomes over the total outcomes, but that's only if you have equally likely cases. In general, you have to use the and or rules. Okay, so the and or rules are based on conditional probability. Conditional probability is that you're imposing a condition which defines the denominator, which defines a subset of the sample space called a conditional subset. The part in the numerator is the part inside that subspace. So the subspace of the subspace that meets the event criteria. Okay. Right, there is a formula for it, but we really never use it. We do it by drawing out the sample space in some way, right? And sometimes conditional probability is hard because it's backwards through the tree. But if you just think of it as there's outcomes at the end here, and some of those outcomes form the conditional sample space, this one and this one. So some of the paths lead to that, but then only some of those paths meet the event criteria. It ends up being some of the outcomes at the end of the tree divided by some of the other outcomes, a subset of a subset. Okay, and then for or, I picture a Venn diagram, right? Or means the union, which is why we use this symbol. That would be A or B or both is concluded in or, right? The most general case is that there's overlap, right? That means the probability of A and B is something other than 0 because there's overlap. And this is the or formula. You can remember that or is addition, but you have to remember to subtract the overlap, okay? The special case for or is called disjoint events, also known as mutually exclusive events, and that's when the probability of the A and B occurring together is 0. If that's true, then this term here goes away and we get a simplified version of the OR formula, where it's just add without having to subtract anything. Okay, the AND probabilities are, you can think of it as a Venn diagram. It's the joint probability, but as far as picturing the formula, I picture a tree, right? If you have an event A and then an event B, this is the probability that A happens, this is the probability that B happens, given that A happens, and the probability out here on the end of the tree is the probability of A and B happening. We use the intersection symbol, which is an upside down U. Okay, the general case is that the probabilities on the second branches are changing depending on what happens first, right? So because of that, the AND formula is the probability of A and B is the probability of A times the probability of B given A. It could also be the probability of B and the probability of A given B. It doesn't matter which event you put first, okay? But there's a special case, and the special case is if events are independent. The way we tell that is if the probability of one of the events, like B, is always the same, whether A happens, doesn't happen, or if I even don't consider A and just look at the whole data set, right? And in that case, we get a simpler formula because this is no longer having to be conditional because the probability of B given A is just the same as probability of B. So I can use the simpler version. Okay, so AND is multiply, but the catch is you have to remember the second probability is conditional unless it's the special case. All right, and that's pretty much it. Those 5 things, AND OR rules, they're special cases, and conditional probability, you can solve any probability problem.